Good morning. So coming to this session, I would like to explain the delay parameters like sheet resistance and area capacitances. Since the VLSI circuits consist MOS transistors and MOS transistor structure is a layer structure, in order to estimate delay, you need to calculate resistances and capacitances. So here the resistances are considered as sheet resistance and capacitance is considered as area capacitances. And first of all, let us see how to estimate the sheet resistance value, after that area capacitances values, and then time delay. Coming to sheet resistance, let us consider a uniform slab with the dimensions like width is W, length is L, resistivity is rho, and thickness of that sheet is T. So, okay, that is the different terms related here is resistivity, W, T is the thickness, L is the length between the faces. Now, with reference to this uniform slab of conductive material, the resistance between the faces A and B is expressed as the resistance R equal to rho L by A in the unit of ohms. The resistance between the faces AB you can express as rho L by a very fundamental formula. The resistance of wire having the length L is like rho L by A. Where A is cross-sectional area, where A is the cross-section area, with reference to this slab, that area A equal to width into thickness, that is T into W. So with the substitution of this one in the above equation, the RAB becomes like this. RAB equal to rho L by T into W ohms. Okay. Now, let us consider or assume the considered slab is a square slab. A square slab means its length is equal to width. So that what happens, the resistance RAB is considered for a square sheet. That is referred as sheet resistance. The resistance for a square is referred as a sheet resistance and the notation is RS. Since W equal to L, it is equal to now rho by T. Therefore, the sheet resistance is expressed in the unit of ohms per square. Ohms per square or sheet resistance just. Hence, the RAB also expressed as like this. So you know RAB equal to rho L by TW. Where rho by T is the sheet resistance, and already you know what is the ratio of L by W. It is aspect ratio Z. Therefore, RAB you can express Z into RS ohms. Z into RS, where RS is square sheets. Z is the L by W. Okay. So like that you can estimate the sheet resistance value. Okay. Here is the slide representing that a table gives the sheet resistance value for the different conductive layers which are used in the MOS structures. The conductive layers like metal layer, diffusion layer, silicide, polysilicon, and also two transistors represented, NMOS transistor and PMOS transistor. The sheet resistance of these metals and transistors in different technologies like 5 micrometer technology, 2 micrometer technology, and 1.2 micrometer technology represented here. Okay, you just remember the values of all this. Similarly, the area capacitance is expressed as, the area capacitance means, you know, in the MOS structure, almost the layer separated by silicon dioxide layer, so that you can treat that separation as a parallel plate capacitor. And already you know the parallel plate capacitance general formula is C equal to epsilon A by D farads. Now apply this capacitance value to our mass layers which is separated by silicon dioxide layer, so that you can get the capacitance value. Here in this formula, A is the area of the plates, since we are taking the parallel plate capacitor. So A is the area of the plate, B is the thickness of silicon dioxide layer, with reference to our transistors. D is the separation between the plates. Here plates means substrate and the layers. Okay, epsilon is the permittivity of the free space, and its value is 8.854 into 10 power minus 14 farad per centimeters, and epsilon of insulative is relative permittivity of the silicon dioxide layer, which is equal to 4. And for different layer capacitances represented in the table here in terms of picofarad per square micrometers, the different capacitances, the possible capacitances are gate to channel, diffusion, polysilicon to substrate, metal 1 to substrate, metal 2 to substrate, metal 2 to metal 1, metal 1 to polysilicon. The capacitances again represented in terms of picofarads per square micrometer. In that case, for every value which is not in bracket, for that you need to multiply into 10 power minus 4. Whereas the value represented in the bracket is known as the relative value. It is a relative value. Okay. Whereas the value which is not in bracket is referred as area capacitances for the different types of capacitances of the mass transistor in terms of in the unit of into 10 power minus 4 picofarad per square micrometer. So in the calculation you need to use these values for the area capacitances. And in the VLSI circuits case, the square CZ is considered as the standard unit for the capacitance. The square CZ, whatever the capacitive structure, whatever the capacitor is formed, or whatever the layers for the formation of the capacitor, the capacitance value commonly represented with the standard unit known as the square CZ. It is defined like the gate to channel capacitance of a MOS transistor which has equal length and width. That is a standard square transistor, and the unit is denoted as square CZ. And the square CZ value varies for the technology to technology, which is given, that is the square CZ value is 0.01 picofarad in case of 5 micrometer technology, and its value is represented as 0.0032 picofarads in terms of 2 micrometer technology, and in case of 1.2 micrometer technology the value is like this, 0.0023 picofarads. So in order to estimate, initially we calculated the capacitance value in that square CGs. After that, based on the technologies, to represent in terms of picofarads, you need to use this much of a value instead of square CGs, right? And the delay unit is here called tau. It is defined as the product of one sheet resistance into one square CZ. For this, a model transistors diagram represented here. the pass transistor, whatever the pass transistor here drawn, it has equal length and widths with the resistance 1 Rs, which drives another transistor of NMOS. It is also having same length and width, and it is the load for the first transistor, providing a capacitance of 1 square Cz value. So this is the resistance Rs and this is the capacitance Cz existed in the circuits. Therefore, the time delay or time constant of this circuit is resistance into capacitance, that is 1 Rs into 1 square Cz. That is the time delay, and with the reference to technology, the tau is, in the 5 micrometer technology case, it is 0.1 nanosecond, whereas in 2 micrometer technology case 0.062 nanoseconds, whereas in 1.2 micrometer technology it is 0.046 nanoseconds. The values of tau here is based on the technology like this. Okay, just to remember all this. Okay, and in the next class we can see how to drive the large capacitive loads. If the capacitance is high, the delay is large. So to avoid the delay, large delay, and to speed up the system, what type of concepts you need to use to drive the large capacitive loads, that we can see in the next class.